Thank you, Dipanjan. Thank you, Santosh, for setting this all up. Good morning, everyone. We will be talking today about our own sun, right? I am not sure if you have had any lectures before listening about the sun. So, can everybody mute their microphone, please? Okay, thank you. So the way we'll do it, I have prepared for 2 lectures, and we'll take it very slow so that you have a fair idea of what actually we are all talking about and see how much we progress. And I have different stop points where we could all stop and say that's all about sun. So I'll be teaching you today, or rather I'll be talking about the sun today and tomorrow again at the same time. What I will do is I would request you to just raise your hand. That option is available. If you just click in the where is the raise hand option? I think it should be in the.
It's under the reactions, Durgesh.
Under the reactions, yeah. Under the reactions, you can just click on raise hand, and I will see who has raised hand, and then as and when I feel that I should take questions, then I'll take those questions right away. So you can unmute yourself and ask your questions. Right. So, oops, sorry. Okay. So when we talk about the sun, we start with a phrase which is called living with a star. Okay. And we have a very specific meaning about living with a star phrase. And certainly we do not mean living with one of these stars, right? I mean, you might find it interesting, but unfortunately that's not the topic for today, right? The topic for today is the living with the star, in the sense that we have to live with the star, which is our sun. And living with a star essentially means that no matter what we do, we have to manage and we have to live with the ambience which is provided by the sun, and we have to deal with it. And what is shown in that animation was the sun's radiation and the particles coming all the way, traveling through the interplanetary medium, going all the way to the Earth and beyond till heliopause. Heliopause is the region where the influence of the sun essentially becomes negligible. And as you can see here, so this should run again. Let me try. So you see all these radiation and particles are just going out, traveling through the interplanetary medium, affecting Mercury, Venus, and then coming to Earth. And Earth has this magnetosphere, as you can see. So the day life, the day side is towards the left and night side is towards the right. And the sun's wind and the radiation pressure is just pushing the magnetic field of the Earth. And then sometimes if the orientation of the solar magnetic field is such that it's connecting with the Earth's magnetic field, then it pushes the particles within our own atmosphere, and you start seeing these ring currents, as you could see towards that polar side. If I can stop at some location. Now this is what happens with the animations. So we might have to wait for a second to run. So that's what we mean by living with a star. Now, if we had to live and manage with what the sun is providing us, then obviously what we need to do is to try to understand what the sun is doing, how the sun works, and can we try to understand and the radiation and its changes, and eventually its impact so that we could be better prepared for any space weather consequences or any other consequences which we might have to feel. Now, having said that, that is something which is a sort of a practical region to study our sun. The other reason for studying our sun is that the sun is the nearest star which you can observe. So if you understand the sun to an extent possible, you can extrapolate that knowledge to other stars, right? So you must have heard about HR diagram during your school so far, and as you would have seen, the sun is nothing but just a star, a normal star, which is staying within the main sequence, and there are of course other stars with larger mass and smaller mass and all that. But at least for G-type stars, you can try to understand what the other stars are behaving and try to extrapolate your knowledge and try to study other stars. Okay, now since it is so close by, you could also consider this to be a laboratory, right? Because you can see things in such minor details that you could consider. Of course, it cannot be a controlled experiment, but the boundary conditions are provided by the sun. All you are seeing is the result of those experiments the sun probably is doing. And then you can then try to infer what the physics is going on. And studying the sun is not only related to studying the astrophysical objects, but also various ranges of physics. So let me just outline some of the things which are related to are sort of you can combine the solar astrophysics with other branches of physics. So one of them is, as I mentioned, the sun-climate relations, the sun-earth relations, climate and space weather. So sun, of course, provides the particles and radiation, as I mentioned. And it has short-term effects, which is weather, space weather. For example, if you have heard of aurorae being seen at very low latitude, electric power blackouts, astronauts going into space, and so on. But also on a very long term, the same weather thing can go into a climate physics, whereby you try to understand that over centuries or over millennia, how has the sun's radiation affected the climate pattern on the Earth. Then turbulence and dynamos. We know that, and I'll allude to later on, that sun has a dynamo which produces magnetic field, and it's a turbulent dynamo. The whole atmosphere, at least the lower one, is highly turbulent, and therefore you can consider that as a turbulence laboratory and dynamo laboratory and try to understand the physics of those. Plasma physics, of course, is fully ionized in the upper atmosphere, partially ionized in the lower and middle atmosphere. So you can try to understand the plasma conditions and derive some plasma physics. Atomic and molecular physics, for example, is helium. Helium is second most abundant element in the universe, but it was first detected in the solar spectra during solar eclipse. So that gives an example of how relevant sun is for atomic and molecular physics and detecting different lines, not only ions and elements in general, but also about, I'll tell you later, that you could observe spectral lines which could correspond to really high temperatures. For example, iron 14, iron 15, calcium 17, and so on and so forth. Fundamental physics, neutrino and gravitation. Neutrino, as you know, is produced in the core of the solar in the core of the sun. It changes its flavor while it propagates. It's a highly non-interacting particle, and it has also affected the way the fundamental physics has grown, in the sense that if the neutrino physics, so what happened was like the sun's the physics at the core, the nuclear reactions, if you like, producing a factor of 3 more neutrinos than they were being observed by various observatories at the Earth. And it took a long time, and only till early in late 90s and early 2000, it was understood that it was poor understanding of the particle physics rather than the solar model itself that the neutrinos were not discovered, because the neutrinos were changing from electron neutrinos to the other flavors. Similarly, gravitation, the first evidence of GTR, or general theory of relativity, came from observing solar eclipses by Eddington. Other branch, cool star activity, structure evolution, which I mentioned already. Solar planet, extrasolar planets. Sun has planets, and you know that all the planets are in the ecliptic. They move around. So how did they form? What sort of effects the sun has? What is the habitability zone? Why life exists on Earth and not on Venus, for example? How actually you can extrapolate and figure out if you are detecting various solar system or stellar systems in the universe, then one can try to figure out what is the habitability zone, how is the atmosphere and the radiation from a given star is going to affect the environment and the ambience at different planets, and also the formation of those planets and so on. And lastly, cosmic ray and local interstellar medium, that how actually cosmic rays come from galaxies, and because of solar magnetic field evolution, solar cycle, how do they get modulated, and so on and so forth. So it's a whole zoo of physics which you can incorporate by studying the solar physics and its sun's properties. So it just depends on you that which direction you want to take it to, and which way you want to do your science and combine that with solar astronomy and learn things from solar astronomy, extrapolate to other branches. Now, sun in our solar system, this is the sun, and all these planets are put on a scale here, and this is your minuscule Earth, and this is put in size. It's not put in the way they are appearing in the orbit, and you can see that it's a tiny object. And what I like to, this is showing Pluto here. You know that it's no longer a planet. Poor guy, he had to be left out of the family. He's still in the family, but it's not one of the main character in the family of the solar system, if you like. And I like to make a statement here that if the Earth is so small, you can imagine how small we are within the solar system. And if you consider yourself and put that on a scale with the whole universe, then we are all non-existent, right? So we have to take this as a sort of thing for humanity, if you like, that, if we are all non-existent, then why to bother and get things, I want to do it first and so on. Just do it and be good for humanity. Right, so why do we study sun, right? So sun is a normal star, as I mentioned, 4.5 giga-years old, main sequence star of a spectral type G2. And I'm assuming that you know all this, spectral type and all, because you have had course already on Introduction to Astronomy. As I mentioned, here is the G-type star, and this is HR diagram. Luminosity is going up on y-axis, temperature is going left on x-axis. And as you can see, there are different stages of evolution of a star. Our sun, which is staying here, it will eventually become a red giant, and then it will just move along this, and then it will come down and rest in peace here as a white dwarf. It's a special star because this is the only star on which we can resolve things on the special scales on which fundamental physical processes take place. Here is an example. This is an image taken from Solar Dynamics Observatory, and what you could see here, 1 pixel on this image could be 500 by 500 kilometers, right? So what the structures you can see is about, if you take all the PSF and spectral and the spatial resolution altogether, then you are resolving structures which are about 1,000 kilometers, right? So all these threads here you are seeing, they're real, and they could be as thick as 1,000 kilometers, and you can see how detailed we see if of any structure we see in the solar atmosphere. It's a special star because it provides almost all the energy to the Earth. This is a no-brainer. I mean, our life depends on it. And the sun is a special star also because the activity on the sun could have devastating effect on the Earth. As I mentioned, for example, aurorae and geomagnetic storms, which are coming from the sun, shaping the space weather. And now, since particularly in India, and of course the northern countries and the polar region countries are much more affected than us. But since we are also getting into space technology, our life depends on satellite communication. It's highly important that we understand how the solar activity is affecting. And it's a unique star because it provides us with natural laboratory to study the fundamental, different branches of physics. So now the sun, as we know, when we are in school, we draw sun like that, of course, without sunglasses. But if you are a much more imaginative child, you will be drawing with sunglasses, and why not? And I'll show you later on that the picture we portrayed in our kindergarten or in schools of the sun, this is how the sun is. Later on, we got modulated by some textbooks where it was shown that sun looks like this, but this is not the complete picture. What we have is a more complete picture than this itself, and I'll convince you later on that why it is so. So this is how we know the sun as we see it from ground, that it's an orange ball. It has number of spots. Of course, that depends on the solar activity, which I'll allude to a little in a while. But all you see is an orange ball. Of course, there is a darkness around the limb area, and it's bright near the disk center. And that is essentially telling you that if you think of a ball, a really, really big ball, and your line of sight is going and penetrating towards the center and going towards the limb, then the line of sight your line of sight towards the limb is much longer than the line of sight towards the disk, right? So if you have different gases which are distributed between you and the sun, then the amount of opaqueness you are getting while your line of sight is going towards the center of the sun is smaller than towards the limb. Therefore, you start getting this darker because there's a lot of absorption in between. And that is true because anywhere you look, there's a sort of symmetry. There's a circular symmetry here, and you can draw sort of concentric circles where you have more darkness, more and more, and uniformly dark regions around the limb. And then on top of that, you have all these sunspot regions, which are really, really dark regions, and they look dark because they are just cool. And you also see fragmented regions around here, and this will become more clearer when I show you much better observations of the sunspots. And then top of that, you have these brighter regions, which are called faculae, which are very important when you start considering the different regions of the sun contributing into the total solar energy contribution, and then its effect on the Earth's atmosphere. Now, there is a question by Ankush Tilekar. Can you go ahead and ask your question, Ankush?
Hello, sir. It's Anushka Tilekar.
Sorry, Anushka. Yeah.
So, can you please elaborate a little again on that line of sight thing that you just said, the length of line of sight?
Okay. So let me try this. And there was a feature here which I could use to annotate. So let me just go out of okay, this annotating thing is not working. Okay, so what I actually meant was that if you take a ball, for example, and draw a circle on a piece of paper, right? And you sit yourself at one location, and you draw a straight line which is going at the center of the circle, right? So hitting at the face of the circle, and then draw which is going touching the limb of the circle. So by the time you touch the limb, that distance will be longer than the distance between you and when it is touching the center part of the circle, of the arc, right? So that distance will be smaller. Therefore, the line of sight you are traveling is smaller, and that's why the radiation looks brighter over there and darker towards the limb. I think it will become clearer when I have another drawing, which will come later on. Is that clear? Okay. Am I still audible, Anushka? Okay. All right. So now here, whatever we know so far about sun, we have put in an artistic way to make it more clearer. So what we know here is that you have the nuclear burning at the center of the sun, and then the energy radiates out. Due to radiation, this is the bright region here. So this is the radiation zone. And then when the radiation passes through this region, when it goes further up, at some point, the temperature gradient becomes so large that the radiation does not work as an effective mechanism for heat transport. Okay, so what happens when you have a very strong temperature gradient? Then there is something called convection that sets in, and what it does is that the plasma parcels, which are heated up here because of the radiation coming from the core, they just decide to take the heat up by themselves towards the surface. They don't wait for the radiation to just take it away, but the whole plasma parcel just comes out on the surface, and then it cools down and then goes back. So it just becomes a cyclic process. Okay, so heated plasma goes up, and then it cools down, goes down again, gets heated, then comes up again, and so on and so forth. This is the convection cycle. How do we know that? Have we seen this? We have seen this. So if you look at this, this is an observation taken from Swedish solar telescope. What you're seeing, these are the bright regions here. They are called granules. And what you see, these are the hot plasma parcels. They're coming up and then cooling down, and then they're going below again in these dark lanes here. Right? So any plasma parcel you see, this is bright, and then around this, there is a dark lane here where this just the plasma is going down. Okay? So that is what we know. That's the convection. These are the convection cells, essentially, they are working. If you do a Doppler imaging of this, so for example, if you take a spectral line and you measure the line shift, right? So you know that the spectral line will shift either towards the blue side or towards the red side, right? So if it is moving towards the red side, that means it's going away from you. The plasma is going away from you, right? And if it is shifting towards the blue side, then it's coming towards you. So what you see, that the line is moving towards the blue, and then it's moving towards the red. So it just does like that. So what's happening is that this region here, in this, it is, you see blue shift where the plasma is coming up. And if you measure at these dark lanes, then you see that the lines is shifting towards the red. Now, right. What else do we know? We know that this region here is as the surface of the sun, right? That's your orange ball, right? What we see here is this orange color. Now here we have removed, because we know that what the line of sight effect is and how the Planck function varies, then we can just model that and remove all these dark regions, because that is actually artificial anyway, depending on your line of sight. So we can remove that, and we see that it's a complete uniform homogeneous orange ball. But on top of that, you have all these dark regions. Okay. Now, this is the region, it's called photosphere, and it's called photosphere because the photons from there, actually they fly away. So what happens here at the center, you have all these nuclear reactions going on. You produce photons, right? In the nuclear reaction, you produce photons, which are at gamma rays frequency, right? They are very, very high energy. By the time they travel to the surface, which is this, they become visible light, and that's how you see it from ground, right? They become visible photon. So their wavelength increases, right? That means they're becoming lower energy photons. What happens that they become lower energy? Because the density in the solar interior is so large that their mean free path is very, very small. So any photon which you generate here, by the time that photon comes to the surface, it can be about 1 million or a few million years, right? It will have to go through various level of interaction inside the sun, and it becomes visible light. So whenever there's an interaction, the collision, it loses its energy, and then it becomes lower and lower energy photon, and then you start seeing visible light when it finally comes to the surface of the sun. And that's what it takes from this surface to you. In about 8 minutes, it comes and gives you the sunlight. And on top of that, as I said, you see all these spots, which are sunspots. Okay. Now, what else do we know? What we could also do, that from the same filter, same telescope which we are using from ground, we could use different filters. Like when you take photographs, you can choose different filters. Similarly, in the telescope, we can change the filters. And when we change the filters, of course, depending on the solar activity, what we find that the sun looks reddish because this is taken in H alpha. H alpha is something like 6,000 something angstrom, which is going towards the red, and it looks red. And what you start seeing here is a lot of structures which are dark here, which are called filaments. And you also have these brighter regions, which are called plazas, right? So these are all names. But what essentially you have is that this is a plasma just supported by magnetic field. And why it is looking dark? Because there is a radiation coming from the background. And this is cool plasma. So it's just absorbing that radiation. And you see that as dark when you are seeing is on the disk. But if the same structure appears on the limb, for example here, that appears in bright. Why? Because there is no background radiation. This is coming from the limb of the sun. There is nothing in the background which is emitting. So what you see that this structure itself has some radiation coming out. The radiation and the temperature is smaller. So when you have the disk, which is a lot more radiating, it's just absorbed by these structures. So they look dark. But here they are emitting themselves, and that's how you see them as bright structure. Okay, so that is what is called prominence. So the same structure, two names, filaments and prominences. Okay, and that is what is replicated here. This part here is just put in as a chromosphere. It's called chromosphere. Chrome means red in Greek, and that's why it's called chrome. And it's a sphere around the photosphere, and it's called the chromosphere. Okay, and then you start seeing filaments and other structures within the chromosphere as well. Then what else we know? Then moon comes and blocks the sun, right? And that happens during total solar eclipse, right? I mean, there are different kind of eclipses, you know that. But during total solar eclipse, when the moon comes and blocks exactly the sun's disk, then what you start seeing is this whole structure outside. This is about 1 million times less bright than the disk of the sun. And that is why when the disk is up there, you don't see what is outside. But when you block it, then you start seeing what is outside. And that's when we see these prominences. And then we start seeing these large scale structures, which are we call helmet streamers. We also see these whole kind of regions. So you have these structures localized here. This is structure localized here. But there are regions when there are no structures, and these are called coronal holes. They are called streamer belts, and so on. Right? So this is what we know from the ground-based observations of the sun. If you go further details, then of course we know a lot more how different individual elements evolve, how their physics is changing, how is the plasma parameter changing, and so on and so forth. But once that is blocked, then you start seeing the outer part of the atmosphere, and that is called corona. That's a solar corona because it looks like sun wearing a crown. And this is a real image of solar corona taken during solar eclipse in 2006. Okay, so what you have, this is the moon, which is dark region here, blocking the sun's disk, and you all start seeing this streamers all around. And this region here, you see these straight lines which are going, they are called plumes. Okay, and they are within the regions when you have the, for example, here, it's the coronal hole. This is a really sort of less resolution image put in here. But if you see into better resolution images, then you start seeing these are the hair-like structure which are protruding out from the sun. What it turns out that this is the north pole of the sun, this is the south pole of the sun, and this is the equator, and all these structures are then in the equatorial belt of the sun, whereas the two poles remain intact in the north and south. Now, the question is, what makes the solar corona so bright, so high up? Right? Why this structure is very bright, and why so high up it's just getting that bright? And that's a question which people have thought about, people have tried to figure about, and is still a problem for scientists to that exactly figure it out. Okay, I can take a question from Deepa. Deepa, you want to unmute and ask? Okay, no, so let's go ahead. So what are the range of parameters we're dealing here, right? So we have solar interior, then we have solar atmosphere, and then we have solar wind and heliosphere. One thing I did not mention here. Now, here, this is the solar corona, but if you go further beyond, then it's the heliosphere. Helio means the sun, and the sphere means the sphere of influence of the sun, and that is called the heliosphere. And I mentioned heliopause because that's where the effect of the solar radiation, solar particles, that becomes negligible, and that is what is called heliopause. You might have heard in newspapers about a year ago that Voyager 1 and Voyager 2 just crossed the heliosphere, or just went out of the solar system. What does it mean it went out of the solar system? There is no one boundary for the solar system. It's just the heliosphere that too is not a specific one particular line where you can say, okay, this is where the heliosphere is. There is an approximate range where you can say that, okay, by this, the effect of the sun's becomes minimal, and therefore we can call it a heliopause. And then the Voyager spacecraft went out of the heliosphere. And now, if I have to put all the numbers onto scale, what we're talking about, if you're going, that's the 0, center of the sun. We're going 10 to the power 13 is here. I think this is Earth, and this is the magnetosphere, and it's going further away. That's the distance. And the densities, for example, if I put at the center, you have 10 to the power 32, and we are going all the way up to 10 to the power 5, and further lower and lower and lower. So it's like a huge scale. If you have to start dealing with the sun and all the planets and the heliosphere in the same model, if you have to put in, then the scales you have to deal with humongous. And that's what is a challenge for people who are trying to directly simulate that how does the solar activity, how does the solar atmosphere changing and affecting different kind of planets, and then when people trying to project it for different stars, then they are trying to model that how is the habitability zone, and how is the sun's magnetic field or stellar magnetic field is going to affect the magnetic field of the given planet, and so on and so forth. Now again, the solar interior, as I said, the core, hydrogen burning, helium produces gamma rays and X-rays, the radiation zone, and then you have, they become all the way to ultraviolet, and then eventually it goes through the convection, and here is the granulation. Okay, and that's what brings it to the photosphere. This is again an artistic picture, artistic drawing, just to put things in a perspective. Now, there are different techniques people use to study sun. One thing, of course, is you want to figure out what is happening within the core of the sun or the solar interior, and then what is happening outside in the atmosphere. Now, we can certainly not see what is happening inside the sun, right? But that does not mean that we do not know much about what is happening inside the sun. As I already explained to you, there are many things which people know what is happening deep inside the sun. And there is a technique called helioseismology, which actually looks at different kind of wave modes which are generated inside, and some of them it travels to the surface, and then they look at the properties of those wave modes on the surface and try to infer the parameters deep inside the sun. And there are different kind of wave modes. So one of the most important ones are the P mode, and the P mode is just essentially a sound wave with a 5 minutes oscillation. You know the sun is oscillating at 5 minutes, and you can look at how does this 5 minutes oscillation changing. Now the sun has different structure. It has sunspots, it has umbra, penumbra, it has faculae. So what can you do? So what you do is you create models of different sound waves, and the effect you introduce by introducing different kind of structures into that, and then measure it and map it with what the sun should be showing. And if that matches, then you say that, oh, the structures you're looking at may have such and such structures inside and such physics inside to give you such kind of wave modes which you are observing. So that is helioseismology. Then you have magnetography, which is essentially G-man effects and spectral lines. What you do is you look at different spectral lines, and the spectral lines which are more magnetically sensitive. If there is a magnetic field, then that line will start showing splitting, that line will start showing polarization, and then using that, you can directly measure magnetic field on the surface of the sun, and even in the atmosphere, which is much more challenging, and I'll tell you why. Then you have spectroscopy. So spectroscopy and magnetography is not very different, but spectroscopy is dealt with mostly deriving plasma parameters such as temperature, density, flows, where you can look at different spectral lines which are forming at different temperatures, and then you can work out the plasma properties and then model the atmosphere accordingly to understand its physics. And then, as I said, that you have to do modeling. So that is another branch where theoretical modeling and numerical simulations are coming to utmost importance to try to figure out what's happening and why do we observe such things in the solar atmosphere. Okay. So now we know magnetography. What we could do, we could measure, and the sun is so close by that we have a lot of photons coming. So we could measure magnetic field at each point on the surface of the sun. So if I take one point here, measure magnetic field, I can take this point here, measure magnetic field. So this is what you see from the surface. So this is your visible light sun, and this is your magnetic field map of this particular sun. What you see that this is the sunspot region, right? This is another sunspot region here, a group of sunspots. So wherever you have these sunspot regions, you have a stronger magnetic field. What is stronger? More bright is more strong magnetic field, and this is positive polarity, and the black is negative polarity. That means that the field is coming towards you from the positive and going inside the sun from the negative. But on top of that, although you do not see much structures around here, there is a lot of magnetic field all around on the surface of the sun, right? So you can imagine it's like a pizza where you have salt and pepper all over the pizza, but on some locations you have some cheese bursts or whatever you have put in localized, and that's what your sun is, right? Now, this magnetic field is the region that these sunspots are dark, right? And why it is dark? Because the magnetic field, because if magnetic field is essentially, as you could see, that these regions are all because the heat is coming through convection from deep inside to the surface, right? And that is what is radiating, and you see that, right? Now, if you have a strong magnetic field localized at one particular place, then what it does, it stops the convection to pierce in, and therefore no plasma comes up. And since the plasma is not coming up around this line here, although it's still hot, hotter than you can sustain, it's roughly like 4,700 instead of 6,000 degrees, this region starts looking darker. And since also the plasma is not coming in very much, the density is smaller, so you can work out the total density and temperature together makes it an effect that the sunspots region becomes darker. Now, let's take a question now. So, Saurabh Pal has a question. You have to be quick. Okay, Zunich Sengupta. Kausik Bhanja.
Hello, sir.
Yeah, is that Kausik?
Yes, I'm Kaushik.
Yeah.
Yeah, sir. Thank you for your lecture. And sir, my question is, could you please elaborate the heliosphere once more?
Heliosphere is like when you have a charge, for example, right? It has an electric field, right? And there is a region around which the electric field is there, right? So that's the sphere around which the charge has its field affecting, isn't it? Similar analogy you can take that the sun has its effect. Sun has its field, right? It's a radiation field. How much till the distance it is giving, it is having its effect is called the heliosphere. Okay, so all the planets and everything is interplanetary medium and everything is part of the heliosphere. Okay, all right, let's move on. So solar atmosphere. If you have asked your question or did not want to ask your question, please please lower your hand. The name I've already called, I'm not going to repeat, so please lower your hand. Now, the solar atmosphere, as I said, this is your photosphere, and you have limb darkening. I explained it to you, and then you have sunspot regions. Then you have the solar atmosphere, as you see during solar eclipses. Now, the questions which you want to ask is like, is the sun solid, liquid, or gas, or plasma? If you know the density of that gas, then you know what it is. How big is the sun? Mass and radius, if you know, then you can figure out, because you know the density, right? You know the radius, you can figure out how heavy, and you can measure the radius by parallax. What is the sun made of? You do a spectroscopy, you can work out the chemical composition. What is the temperature of the sun? You can do a spectroscopy. Again, like a Planck function, you can fit in the Planck function and get the temperature. And what makes the sun shine, right? That is the most important question, that why does the sun shine, right? Why sun gives so much of energy? So this is the chemical composition part, where you take a spectra, right? And this is in the background, it's only 3 or 4 colors are shown here. is Vibgyor, nothing but just the Vibgyor, right? The rainbow. But what happens if you do high resolution spectra, which Fraunhofer did, what you start seeing is these dark lines on top of this Vibgyor. Now, what does it mean? These dark lines are essentially telling you that there are no photons at those particular wavelengths, right? So if the wavelength is going this way, then essentially the photons at those particular wavelengths are frequencies missing. And any photon missing, the sun is not making a partial emitting of photons. Sun is emitting at all these visible light range. So what happens is, like, you have different kind of gases in the atmosphere, and they essentially absorb those photons. Now, absorption or emission is a specific property of any element. So because any element cannot just randomly emit or absorb any particular photon, right? So if you know at what frequency these photons are getting absorbed, and you know from laboratory that in visible light, in a rest frame, how does the spectra should look like, you can always compare and then figure out that these lines, they belong because there are some certain elements within the atmosphere which are absorbing those photons. And therefore, you know that what is the chemical composition of the solar atmosphere. Okay, helium was an emission line which was discovered in 1896 by William Ramsay in solar eclipse spectra. So by doing this, there have been 20,000 lines identified in the solar atmosphere. Now that means there are not 20,000 elements. It's just that there are different ionization states for different elements. And depending on their ionization states, they emit and absorb different kind of photons. And therefore you can assign those to different elements. Temperature, as I said, you just measure the radiation density as a function of wavelength, or as a function of frequency, and then you can, depending on how does the spectrum look like, it can be uniquely fitted by a single temperature Planck function, right? And if you can fit that, that means that the structure or the object you are looking at is a black body, and therefore you can assign a unique temperature to that particular body. And in solar case, that's the structure, that's the Planck function, which actually fits in well with 6,000 degrees. And then you know that the sun is a black body emitting at 6,000 degrees. Now, what makes the sun shine? This is much more profound question. And you know that is because of the nuclear burning, but how does it work? So let's look at some numbers. So the total energy output from the sun is around 3.8 into 10 to the power 26 joules per second. Okay. Now, each square centimeter, so any square centimeter you take from the sun, is as bright as 6,000 stars, or probably brighter than 6,000 times than a torch, right? Or 6,000 torches burning together. And then it delivers, that means 1.36 kilowatt per meter square, right? That is a solar constant. If you remember, 1368 watt per meter square is the solar constant. I'll tell you later that it's no more a constant. It has some variation with the solar cycle, but very little. And for practical purposes like ours, not ours, yours, people who consider sun as an object which is giving us light, for them, this could be considered as a constant. So if we take this into account and work out that how much energy the sun is producing, in about 20-30 minutes, the sun provides to Earth the yearly needs of humanity. How much is the yearly needs? 5 into 10 to the power 20 joules per year, right? So the whole humanity, the amount of energy the whole humanity uses is 5 into 10 to the power 20 joules, which is smaller than the sun produces in a second, right? And that is why so much of emphasis on solar energy and saving and using solar energy for humanity. But the question is more specific we are dealing with here, that how does the sun manage to produce so much of energy? And that is essentially, it takes you to this. Let me just tell you here. Oops, sorry. Right? So what happens is, like, you have two hydrogen atoms coming together, converting into 3 He and a proton, and then you have 3 He combining together, then essentially producing 1 helium. So what you need, 4 hydrogen. So one hydrogen giving you 3 He, and then one hydrogen, the other hydrogen giving you 3 He, and then these two 3 He's coming together, forming 1 helium and leaving rest aside. So what you get, 4 hydrogen converting into 1 helium, right? What does it mean? So 4 hydrogen is heavier than 1 helium, right? So in approximation, what you can take is like the total mass deficit, right? So 4 hydrogen converting into 1 helium, and the rest of the energy is released. The total mass deficit is essentially converted into energy by E equals to mc square. And since it's a tiny mass, but you are multiplying with the c square, then the energy released becomes really large, right? And it's not just 4 hydrogen are at any given time. So every second, the sun is converting about 1 billion ton of hydrogen into helium. And that's how it is producing so much of energy, which we observe and measure. And for that, the temperature at the core, at the center, becomes about 10 to the power 15 million Kelvin for the nuclear reaction to start. And how does it work? Because the sun is a gravitationally collapsing body. What essentially it means that this guy here is just getting collapsed by this ball on his head, right? So from all direction, there is a contraction. The gravitational contraction is going on. And because of the contraction, the temperature is increasing and the density is increasing at the center of the sun. Essentially, you can take an analogy that when you are filling air in the tire of your cycle, what happens? You keep pressing air. Because of the high compression, the temperature becomes larger and larger, and the density is getting larger and larger. And because it's happening on a much larger scale at the center of the star, of the sun, that becomes much high, and then the temperature and density becomes large, and it breaks the Coulomb barrier, and then 2 protons starts coming together, and that gives you 4 He plus 2 proton and some release of the energy. Okay. Can we work out? Can we get some numbers? So this is like the pressure at the center of the sun equals the weight per unit area of the material on the top. So if you take the sun like that, in that column, weight per unit area will give you the pressure at the center of the sun, right? Now let G be the average gravitational field felt by such a column of material of mass per unit area m. Then in order of the magnitude, you get small g, which is gm of the sun over r of the sun square, and therefore mass m will be equals to ms over rs square. Then you can work out what the pressure is, this mg, and then this quantity here, the pressure becomes this 10 to the power 17 grams per centimeter per second square. Now, what you get essentially, let me just put you in now, if you consider the whole thing as a ideal gas, and if we can measure the density, which is 1.4 grams per cc, if you put that in here, then the temperature turns out to be 15 million Kelvin at the center of the sun, and that then satisfies the prospects of the thermonuclear fusion, because you have enough density and enough temperature for the nuclear thermonuclear fusion to start. And then this is what it gives. Hydrogen gives you 2 deuterium, and then 2D again combines with H to give you 3 He. Earlier I said 1H give you 3 He. There's another process in between. There's a deuterium formation, and then that gives you He. And now these 3 He combines together gives you 4 hydrogen, 2 protons, and this much amount of energy. Okay, so that's 12.85 MeV of energy. Right. Now that energy is then coming outside, right? By radiation, and then again by convection. And as I said, this is observation. What you see here, this is about 10,000 kilometers long. The biggest structure here, they are called the convection cells, and they are the granulation, and they are the convection cells. They are bringing the heat outside. Now, when you look at so far we've been talking about what you see from the ground. Now, when you go to space and we look at the total solar radiation spectrum, then this is what we observe, right? So when you far from ground, this is the part we will get visible IR and radio, right? So this is visible and IR only. And that is what you fit with the black body temperature of 6,000 degrees roughly. And you say that, okay, sun is emitting at a black body at 6,000 degrees. But when you go up into space, where the Earth's atmosphere is not stopping any part of the radiation coming from the sun, then you start seeing there are radiation coming from the sun in extreme ultraviolet, and also X-rays, which is not shown here. Okay. Now, if the sun was only at 6,000 degrees, which is this part here, then it would not be producing extreme ultraviolet and X-rays. Okay. So there must be some other physics going on which is producing this part of the spectrum of the sun. I said that the sun is producing ultraviolet, but and gamma rays, that is at the center of the sun. It's the gamma rays and then X-rays and then becomes ultraviolet and then this comes out as a visible light. But that is happening at the interior, and all these high radiation here, they becomes visible light radiation while it travels to the surface of the sun. But when you observe, you start seeing this part of the spectrum, and that means that there is something else happening which is giving you this part of the radiation, right? And therefore, it was observed in one of the total solar eclipse, where people started observing spectral lines which are forming at these kind of wavelengths, 5303 angstrom, 5509 angstrom, I guess, and this was the first line which was observed in the eclipse, and people thought that this could be related because they had a success on discovery of helium. They thought that this is coming from the corona. They called it coronium, but they couldn't find any matching element related to this spectral line in the periodic table, right? They started calling it coronium, but then coronium had to find a place in the periodic table, and they did not find a place in the periodic table. This was done in 1860, and in 1940 or so, people like Eldon and Grotrin demonstrated that these lines are not because of some missing element or something, but these lines were essentially because of these kind of ions present in the solar corona. Okay. Now these are the ions which are iron 14, calcium 15, and nickel 15. Why these are important? Because iron 14 means that this is 13 times ionized iron, right? What has been done? That you have taken out 13 electrons from iron. Now you can imagine that how much energy you need to take one electron out of hydrogen. That is your ionization potential. That is 10 point some eV, right? To take away 13 electrons from iron, you need huge amount of energy, That means that the temperature of the gas you are looking at has to be really, really high. Similarly, 14 electrons out of calcium, 14 electrons out of nickel. So really need to have huge amount of energy to ionize or to take away those many electrons from these elements. Okay, and it was figured out that you can only do that if the gas is extremely hot, and it could be as hot as million degree, right? So outside region here, this part, the corona, has to be million-degree hot. While the surface, we said everything was settled, that it was 6,000 degrees, and we explained it with the Planck function, which is well established, but outside here, it has to be million-degree. And why then so much structure? The structure is that if you have million-degree plasma, then all these gases, the whole thing we are observing here is fully ionized. So that fully ionized means there are so many free electrons in the atmosphere. And if you have so many free electrons and you have light, which is the visible light, which is coming from the surface, which is passing through this region, they get scattered with those free electrons. If you have heard of Thomson scattering, they scatter through without changing its frequency and all that. More the electrons, more the scattering. So more the brightness here, more the scatter light you are seeing, that means they have more free electrons, right? So some of these structures are brighter, so you have more free electrons. Some of these structures are darker, that means they have less free electrons. And the structure is because everything is related to the magnetic field, because the surface magnetic field is just giving you lines of forces in the atmosphere, and the free electrons are essentially trapped within those field lines. And therefore, by looking at the eclipse images, what you are essentially getting information of how is magnetic field and free electrons are distributed in the solar corona, right? Such a powerful technique, you can imagine. The whole thing is telling you how are the electrons distributed, and how is magnetic field structured in the atmosphere of the sun. Okay? So this is the existence of hot corona was finally settled. While this part here is 6,000 degrees, this part here is about 1,000,000 degree, which is sitting on top of the. And that is why, if because of this temperature, you have this radiation coming in near ultraviolet, extreme ultraviolet, and X-rays. Now the question is that if you have a surface which is 6,000 degrees, and we know that why it is 6,000 degrees, because you have nuclear burning at 15 million degrees going out, your surface is cooling, the surface is not as hot as the core, but suddenly you jump to 1,000,000 degree, but we don't know what the source of that energy is. And that is actually a major puzzle, that what actually heats this gas to 1,000,000 degree, while this gas is only 6,000 degrees. Now, if I bring this back, this is how your sun looks like, and this is how we used to draw early on, right? So this is a much more complete picture than just this picture itself. Again, the solar radiation spectrum, if you look at this, if you only observe from ground this part here, then you only get information about this part, but you are missing out a lot of information about the physics of the sun if you're ignoring this part. That essentially tells you that you're looking at an elephant by 6 blind men. So if you're depending on the wavelength you are looking at, you could belong to this, you could belong to this, you could belong to this. But unless you put all this information together, you do not know what the physics of the sun is. And that is our main goal when we talk about multi-wavelength astronomy or multi-wavelength solar astronomy, to try to put these information together so that we have a complete picture of the sun. And once we do that, we go to space, because X-ray and ultraviolet does not come to us. We have to go to space to image the sun. And what we find, this is your sun as you know it from ground, but we start taking images of the sun into different frequencies. And this is the sun taken almost at the same time, okay? But using different filters. That means that we have different wavelengths we are measuring, or different temperatures we are measuring. So what we see, as we go higher into the atmosphere, the temperature increases from 6,000, 5,000 degrees to about 4 to 6 million degrees. And the structure or the sun's face looks completely different than what this only one wavelength tells you. So depending on the wavelength, sun looks very, very different. Now, one thing I would mention now, and we'll finish today. What you're essentially seeing, this is magnetic field map, which we generated taking the spectra on this image here. What we find that there are magnetic field scattered all over, as you can see. But if we compare this structure here to all these images here, what we find that wherever you have magnetic flux or the magnetic field stronger, you have the much brighter structures in the upper layers of the atmosphere. That means that the magnetic field is the main cause for all these structures, the brightness and the heating in the upper layers of the atmosphere. But we also know that the magnetic field generated by dynamo deep inside the sun, that means that the whole solar atmosphere is connected through magnetic field in a way that it is producing energy somehow to bring the upper layers of the atmosphere to 1,000,000 degrees. Okay, so with the masses that the photosphere, the chromosphere, transition region is something in between, which I'll tell you tomorrow, and the corona are all magnetically coupled, and the whole thing is very highly structured and dynamic. And with that, we'll finish today. We'll take questions and get back to this again tomorrow from here onwards. Okay, so let me just see who has questions. Okay, Nandini Sharma, do you want to unmute and ask?
Good afternoon, sir. Sir, I want to ask if it is possible to make solar atmosphere artificially.
No, I mean, how would you create such high temperature and ambience at the? So that's not possible. You mean in the laboratory, right?
Yes, sir.
Right. In the laboratory, of course, people are trying to create in tokamak like thermonuclear fusion. They're trying to create fusion reactors so that we have constant source of energy all the time. We don't depend on biofuels and stuff. But that is still work in progress. Generating solar atmosphere is further bigger challenge. Okay, Astha Chaturvedi.
Yes, sir. Am I audible?
Yes.
Yes, sir. Taking account of the compression mass deficit, it is expected for the source function to deviate from the black body function, right? So how are we getting the exact plot as the Planck function for sun?
Right. So we don't get the exact plot of the sun. So let me just go back.
I mean, it's invisible region
here,
as well.
Right. So here, when we observe only this part, right? We only observe this part here, right? So we fit that with the Planck function, right? In this range here. Okay. We don't get the whole thing. We only get this part with the Planck function. So we say that okay, this the sun is in local thermal equilibrium, and then it produces energy by a black body radiation.
Only the visible one.
Only the visible part, yes. So if you take this and zoom it out, then you will find that this is going like that, right?
And what about the IR region? How do we get that?
IR region, you can measure spectral lines from ground, right? So you can find out what the temperature is like.
And it is expected that we don't even get it exact, right?
Yes. Tomorrow I'll show you that, I mean, when you consider that as a simple ball, then of course everything is very approximate because sun's structure varies very differently depending on the location you're observing.
Yes.
So every specific features will have very different temperature structures. Okay, as you said yourself, right? Depending on where you take, if you look in the sunspot, you look in the active regions and look at the quiet sun, then the whole profile could be very different.
Yes, yes, sir. Thank you so much.
Okay, Mehul Chakravarti.
Good morning, sir. Am I audible?
Yes.
So why do we have heavy elements like iron, calcium, and nickel in solar corona?
Haha, that's a bigger question. So we have to go and ask, like, how did the sun form, right? Because all we know is the hydrogen burning is happening and hydrogen is only creating helium, isn't it? So your question is that how do we have the heavier elements? And that is because the sun formed because of other supernova which happened early on. Right? And when the supernova happens, then everything has like all this burning thing had been finished, right? So you all the way you go to the iron core, isn't it? So even you can ask about all these elements which we have in periodic table, heavier elements. How do they come on the Earth? Right? So it's all because there was something else happened before that, and that was a supernova which perturbed the gas which formed the sun. And because of that, we have all the heavier elements in the solar system as well. Right? Why do we have so much of gold, for example? Right? Gold happens only when you have big, for example, you might have heard 2 years ago or 3 years ago in the news that two neutron stars merged together and produced a lot of gold, right? Because of that kind of interaction, you fuse different elements and you form heavier and heavier elements. Okay. Sri Suman.
Yes, sir.
Yeah, go ahead and ask your question. You had a question?
Sir, heliosphere is the effective zone or region of the radiation field. If you want to denote in the diagram as core, radiative or convecting zone, then where will the heliosphere in the particular diagram?
That diagram becomes too small. Then you will, if you have to put that on the same scale, then you will not see anything like convection zone and radiation zone. It is going all the way beyond Pluto, right?
Okay, sir. It means range is so large for the heliosphere.
Correct. Very large. Yeah.
Okay. Okay. Thank you, sir.
Okay, Saurabh Paul.
Yes, sir. So all the data we have regarding the core, the surface of the sun is based on the ground antennas or some satellites we have, but we don't have any probing techniques. So I want to ask the ongoing research of how we can probe in future to the sun for getting better result. Means can you refer one or two direction of research how we can probe to the sun?
We are already probing to the sun. What do you mean probe the sun?
Probe means to hit something on the surface of the sun and getting some direct result from that. I know that is not possible yet, but what's the direction of research? Means is any kind of research is going on how we can reach to the sun surface?
Do you want to go to the sun surface?
No, sir, but I am just asking. Means if we want to get direct results, and that can only possible if we can go close to the sun.
Yeah, I mean we have all the direct research, direct results. The two ways, as you mentioned. So there are two ways of doing astronomy. One is remote sensing, and that's what we are doing. We are sensing it from further distant. There is a mission going on at the moment called Parker Solar Probe. You can Google it and look at it. What it will do is it is going very close to the sun. Every orbit is going closer and closer. It is going up to 10 solar radius, but eventually it will fall on the sun. But the problem is that beyond 10 solar radius, even if it goes further closer, then you will not get any information because it will all burn out. Right? So that will still be distance 10 solar radius away. So one solar radius is 700,000, 7 lakh kilometers. So 70 lakh kilometer away, right? So the best information from your terminology will be there from 70 lakh kilometer away from the sun.
Okay, but further improvement technique can be discovered regarding this.
Of course, yeah. I mean, it took only 60 years to discover techniques to let Parker Solar Probe happen, but certainly there might be other techniques which people will develop, which might let spacecraft to go there. Who knows?
Okay. Okay, sir.
Okay, Vaisak PA, you want to unmute and ask?
Hello, sir.
Yes.
Yes, sir. So when you show the magnetograph image of the sun,
Yeah.
so there were black spots and white spots, right?
Yes.
So do they are actually magnetic field lights coming out of the sun surface?
So the white is magnetic field lines coming out, and the black is magnetic field lines going down.
Okay, sir.
Going
So
in.
are these related to any sort of flaring activities or CMA ejections?
I will talk to you tomorrow about that. Yeah.
Okay.
So those are the regions where the CMEs and flares do occur.
Okay. Okay. Thanks.
Yeah. There was one more hand raised. Who was that? I think I lowered the hand mistakenly. Yeah, Aniket Prasad. You want to go and ask? Go ahead and ask. Unmute.
Good morning, sir. My question was, as we discussed, it was during solar eclipse that we could identify the absorption lines coming from corona. I wanted to know what exactly. Sorry, sir.
Not absorption line. Those were on the disk. I only mentioned that the emission line for helium was discovered from the corona. But go ahead.
My apologies. So regarding that, why is that necessary? Like, why do we need solar eclipse for that? Can't we just identify that in normal spectrum of sun?
Well, I mean, for discovery, you didn't know what was there, so you have to find a region that you see this. But now we know that, so now anything, anywhere we can put in and get the spectrum. Of course. Earlier, when things were not known, then people were trying to understand what kind of gases you have outside in the corona. And to see the corona, you needed an eclipse, right? Because the disk was very bright. But now it is discovered, but then now you know there's all around the sun, we have that kind of gas, so we can do it anytime. We don't need to, and that's how this thing is done. For example, these images, these are in emission lines of these lines, no, iron 14, X-rays, iron 11, and all this. So that is done on the disk. All you need to develop a technology, a telescope, which let only a specific light come inside your telescope.
Okay, so the solar eclipse kind of made a filter, natural filter for us to see the exact lines which we wanted to see.
I wouldn't call it a filter. It facilitated to see the corona.
Okay. Thank you, sir. And one thing more. Are we going to discuss about the solar cycles in coming slides in this lecture?
Tomorrow I'll mention some things, yeah.
Oh, okay. Thank you, sir.
Okay. All right. Aniket, you are done. So, Zurich Sengupta, you want to ask?
Hello, sir. Am I audible?
Yes.
Oh, thank you, sir. Sir, I'm extremely sorry. Last time I couldn't unmute myself. I couldn't ask the question. So my question is, the 5 Lagrangian points around the sun, is the nature of all of them similar?
I didn't talk about that in my lecture yet. Why are you asking?
Okay.
Of course, they're not similar. There are some of them are more stable, some of them are less stable. So depending on what you want to do with those points, you use them accordingly. So for example, L1 is between Sun and Earth, which is not a fully stable. So you can put a spacecraft there, which can orbit around that L1 point, and you can look at the sun 24 hours. But if you want to avoid the sun and look at the night sky, then you can go to L2, which is beyond the Earth, Sun, Earth, and then the L2 point. And that is where the JWST is going to be. L3 and L4 are very, very stable orbit. That's why we have a lot of space debris in L3 and L5 because they are very stable. So anything you put in there, it doesn't come out. So all the debris, they just go there and stay there. So there are, of course, different properties there. But I'm not going to talk about that. That is more like a classical mechanics question, which you could refer to.
Okay, sir. Thank you, sir.
Satrupa Mandal. So Trupa, you want to unmute and ask?
Yes, sir. Hello. Sir,
Hello?
am I audible?
Yes.
Sir, I have the question like why the corona radiation have hair-like appearance at the pole of the sun? Sir, are they just observation or have any particular reason like the magnetic fields over the surface?
Yeah, I'll talk about it tomorrow. But essentially, the magnetic field is kind of straight there, which is coming and connecting the North Pole to South Pole. So I have a magnetic field which is going from here and coming here. So it's going and connecting like that. So here it will be effectively straight, right? So that's why the hair-like structures are appearing like that. But I'll talk to you about it tomorrow more.
Okay, sir. And this sunspots are also due to that strong magnetic fields, which
Yes,
stops the plasma convection process.
Correct. I did mention about it. Yes.
Sir, are they
All right. So thank you very much for today. And I will, why can't I stop sharing? Yeah. So I will log in tomorrow again at the same time and tell you more about sun, whatever we know, and leave you with some open questions, I hope. All right. Thank you very much. Santosh, I'm logging off then.
Sure, sir.
Okay. Thank you. Bye.